So we're going to do the Rangakuta second order method today, and at first we will talk about the background where Rangakuta second order method comes from, and the ordinary differential equation that we are trying to solve are based on the first order differential equation of the form we have seen in the last lecture, which is dy by dx is equal to the function of x comma y. So we know the slope of the dependent variable y here as a function of the independent variable in terms of the function of x and y, and we're given an initial condition y at x0 is equals to y0. Now, if you try to remember what we studied last week was the Euler's method that had the formula yi plus 1 is equal to, someone's microphone is on. Do you want to say me something? So we have yi plus 1 is equal to yi plus the function at xi comma yi times h. But then the Euler's method is not very accurate, and to find a more better accurate method, we need to do something different. So that's what Rangakuta did. In order to find out a better method, they have discovered the Rangakuta second order method, and to do that we need to do something called the Taylor series. So I hope you remember what the Taylor series is, and the Taylor series for a point at xi plus 1 looks like this one here. So you have, just right here, Taylor series. So the Taylor series expansion is at yi plus 1 you have yi plus dy by dx at xi yi from xi plus 1 to xi plus 1 over 2 factorial, the second derivative d2y by dx squared times, or at the point xi yi. I'll just write this down here. So it looks organized. So we have here xi yi from xi plus 1 to xi, and then here it will be squared this distance between xi plus 1 and xi. Then we have plus 1/3 d cube y by dx cube at xi yi from xi plus 1 to xi cubed. So that's what the Taylor series expansion looks like, and we know that dy by dx is equal to f of x comma y. So we will replace the dy by dx in the Taylor series expansion here with f of x comma y, and that will give us the Taylor series that looks like this here. So you will have yi plus 1 is equal to yi plus, replacing dy by dx by f of xy. So we'll have here f of x comma y, or you can say f of xi comma yi times h. So we'll replace the value here xi plus 1 to xi as h because that's the step size. So, or you can say, you can write this here as in different letters. You can say this one here can be replaced by h. So this one here can be replaced by h square, and this can be replaced by h cube. So we have here h plus 1 over 2 factorial f first prime x I y I plus 1 over 3 factorial. Okay, I forgot to write here h squared. Then we have f second prime x I y I times h cubed. So that's how the Taylor series expansion looks like now. And you can see that if you take the first two terms of this expansion here, this is Euler's method, right? So this here is Euler's method. And if you take, let's say, the first three terms here, this is the Rank-Kutta second order method. So this is the Numerical second order method. So it makes more sense that if we want to get more accurate result, we can add one more term here to the Euler's method. And that's why this is called the second order method, because you're adding a second order term here, which is, I don't know if it's clear to you, but you can see it over here, we are adding a second order method, that's d2y dx squared. So you can say that what Rank-Kutta method is based on is yi plus 1 is equal to yi plus f of xi yi times h plus 1 over 2 factorial f of xi yi times h squared. So that would be the formula. But we can see that we'll face an issue here, that is, we have to find out here the derivative of the function with respect to x. So let's suppose that we have a differential equation that looks like this one here, which is e to the power minus 2x minus 3y with the initial condition y0 is equal to 5. Then the function x comma y is this one here, which is e to the power minus 2x minus 3y, and the first derivative of the function will be del f with respect to x plus partial derivative of the function with respect to y times dy by dx using the chain rule. So the partial derivative of the function with respect to x will be minus 2 times e to the power minus 2x, and then you have partial derivative of the function with respect to y, which is minus 3 times dy by dx is e to the power minus 2x minus 3y. So that's dy by dx written here, and that would sum up to minus 5 e to the power minus 2x plus 9y. So you can see here that we have to symbolically find out the f prime value here, and then you can substitute this f prime value back to the general formula to develop the Runge-Kutta second order method. But that's not what Runge-Kutta did. What they did, or what they wanted to do, was to find out a formula where they do not have to find out the derivative of the function. So they wrote down the equation, or you can say the formula, to do the Runge-Kutta. I'll write in the next page here, maybe better, like this, which is yi plus 1 is equal to yi plus a1 times k1 plus a2 times k2 times h, and k1 is the value of the function at the point xi, yi, and the k2 is the value of the function at a certain point, which is xi plus r xi. Okay, comma p1h here. I'm writing something wrong. Xi plus here, and comma yi plus q11 times k1 times h. Okay, so this one here is supposed to be xi plus p1 times h. Yep. Okay, so now here the values a1, a2, p1 and q11 or q11 are unknown. And what Runge-Kutta did is they took this equation here and equated it to the first three terms of the Taylor series expansion, which is here, the first three terms of the Taylor series expansion. And they found out that they got three equations which looked like this one here, which is, I'll write in a different color maybe. So the three equations that they got by equating those two were a1 plus a2 is equal to 1, a plus or a2 times p1 is equal to half, and a2 times q11 is equal to half. So how they equated and they came up to this is not something that I want to teach you all, so I'm avoiding that part. And once they came to these three equations here, it is, you can see over here we have four unknowns. So we have four unknowns here, a1, a2, p1 and q11, and we have three equations here. So that means that one of the choices can be made by us. So this is the reason that there are several different methods of Runge-Kutta second order method, and out of those there are three popular choices which people use, out of which again we'll only learn two. So the first popular choice that people use is the Heinz method. So that's the two methods you learn is the Heinz method and the midpoint rule. So the first one is Heinz method. Okay, before I go ahead, maybe do you all understand everything until now? Is it okay? This is kind of just explaining how they came up with um, with the equation. If you have any doubts, please let me know. So currently we are 27 in the class. Okay, now, so for Heinz method, what we do is, as we were allowed to choose a value, so what Rune could choose for the Heinz method was that A2 they chose as 1/2. And when you choose A2 as 1/2, so I'll just take these equations back so it's more clear. So if you choose A2 as half, then from this one here, you can see that A1 will be 1 minus half, which is half again. So A1 will be half. And then we'll have here our, I'll just show it like this one here. So A1 is half. And now since we know A2 is half here, we'll get here P1 to be equal to 1 here, and Q11 is equal to 1 here again. Okay, so that's just replacing A2 with 1. So you'll have 1 times P1 is equal to, sorry, A2 is half. So P1 is divided by 2. 2 will go on the other side and multiply. So you will have only 1 there. Now if you replace these values here of A1, P1 and Q1 and Q11 and A2 in the general formula, you get the formula as yi plus 1 is equal to yi plus half times K1. So if you remember the general formula again, so we have here A1 times K1, A2 times K2. So A1 as we know is half times K1 plus A2 which shows as half. So half times K2 times H. So that is the formula for the Heinz method now, with K1 is equal to, what it was equal to was the function at x comma xi comma yi. So that remains as it is. And for K2, we have here the function xi plus p1 times h. So we have here the function xi plus p1 times h. So p1 value as we got here is 1. So 1 times h is 1 again. So that will be h itself. And then you will have here yi plus q11 times k1 times h. So q11 we got it as 1 times q1 is q1 again times h. So those are the formulas that you will use for the Heinz method in general. So This is what you'll use for the Heinz method all the time. And from a physical point of view, what you're basically doing in the Heinz method is that you are calculating the value of the slope at the point where you are, which is k1, and then you're calculating the value of the slope of the point where you want to go, which is the k2 here. And then what you're doing is in the Heinz method is that you are taking the average of the two slopes, that is multiplying them by half here and times the h. That's all you're doing for the Heinz method here. And now let's go ahead and look for the midpoint method. So we have, in the midpoint method, we are choosing the value of a2 as 1. So if you're choosing the value of a2 as 1, then a1 plus a2 is equal to 1, the first equation. You will get now a1 is equal to 0 because 1 minus 1 will be 0, and a2 times p1 is equal to half. If you now put the value of a2 as 1, you will get p1 is equal to half. And then you have the third equation, a2 times q11 is equal to half here. And if you replace a2 by 1, you will get q11 is equal to half. So now if we substitute these values here into the general formula for Runge-Kutta method, we are going to get yi plus 1 is equal to yi plus k2 times h. So again, we have here yi plus a1 times k1 plus a2 times k2 times h. So we have got here a1 to be 0, so a1 times k1 is 0 because 0 times k1 will be 0, so we don't write the first term, and k2 times h, so you have a2 times k2 times how do you say that? It's maybe better I take them. So you have a2 times k2, and a2 we got as 1, so 1 times k2 is k2, and since this first value is 0, so 0 plus k2 is k2 times h now. So that's what I wrote here, k2 times h. And for k1 we have the function at xi, yi. For k2 now, copy this part here so it's easier to see. So if you're trying to work with k2 using the values here, you will get the function at the point xi, and then you have p1 is half, so xi plus half h, comma, you have yi plus q11, which is half, times k1 times h. Okay, so this here is the midpoint rule method, and k2 is some approximate value of the slope at the point which is somewhere in between xi and xi plus 1, somewhere in between here, because it's exactly half away from the point you are. That's why it's called the midpoint rule. Okay, so before we start on the examples, do you have any doubts? Any doubts? Okay, great. So now we'll do our first example, that's on the Horn's method. We're given the differential equation, that's dy by dx is equal to 3 times e to the power minus x minus 0.4 y, with the initial condition that f of 0 is, or f at x is equal to 0 is equal to 5. And what we're to find out is the value of y3, and we are given the step size h is equal to 1.5. So the formula for the Horn's method is yi plus 1 is equal to yi plus half times k1 plus half times k2 times h, and then we have, okay, I changed color, should still keep it the same. We have here k1 is equal to f of xi yi, and k2 is equal to the function value at xi plus h, comma yi plus k1 times h. So for the first one, we know when I is equal to 0, x0 is equal to 0. That's given here. This is our x0 and that's our y0. So x0 is equal to 0 and y0 is 5. So we'll use these values now to find out first k1, which is the function value at x0, y0. Okay, so before everything else, maybe I should write here also what's f of x comma y, the function. It's this value here. So it's 3 e to the power minus x minus 0.4 y. And now if we replace the x with x0 and y0, we'll get here, or let me write here, the function at x0 is 0 comma 5. So that will be 3 e to the power minus x0, which is 0, minus 0.4 times y0, that's 5, and this gives us the value 1. Now trying to find out k2, you have the function at the point x0 plus h, comma y0 plus k1 times h, and so we have here x0 is 0 plus h is given to us as 1.5 here. So we have 1.5, comma y0 is 5 plus k1, the value that we just found out was 1. Here k1 is 1 times, we have h, which is 1.5. So that if you solve it further, this value here is just 1.5, comma this value here is 6.5. So we have to find out the function at the point 1.5 comma 6.5, which will be 3e to the power minus 1.5 minus 0.4 times y, which is 6.5, and that gives us the value minus 1.9306. Okay, so we got K1, we got K2, and now we have to find out the yi plus 1, which is y1. So y1 is equal to y0 plus half times k1 plus 1/2 times k2 times h. So you have here y0 is 5 plus 1/2 times k1, and we got the value of k1 as 1 and k2 as minus 1.9306. So k1 is 1 here plus 1/2 times k2, which is minus 1.9306, and the whole thing will multiply by h, that is 1.5. And this gives us the value 4.302 here. Now I want to say you that this is approximately y of 1.5 here, but this is not very clear to write it or to show it to you in this way, which I always prefer is to draw a table. So here, if I draw a table, I values xi, then you have values for k1, values for k2, values for yi. So I need to make a line there. So you have I here, xi, k1, k2, and yi. So when I is equal to 0, xi or x0 was 0, and of course there was no k1, k2, and we got here yi was 5. So the first step, we don't need to know the k1, k2 because y was given to us here. Now if you're finding the second one, we are finding now at I is equal to 1, x1. So what is x1? To find out these values here, I told you that the formula is, if you want to find out xi plus 1, you have x0 plus I times h. So you have here x0 is 0, 0 plus 1, I is 1 now, 1 times h is 1.5. So here it will be 1.5. And for the first one, we found out the k1 is 1. K2 is minus 1.9306. So K1 is 1. K3 is minus 1.9306 here. So okay. And for y1, we just got the value as 4.302. So you can very clearly see that this one here, that is 4.302 now, is the value at x 1.5. The value of the x here is at 1.5, right? So here it is 1.5, the value of x. So now you can see that yes, this is equal to the value at y, value of y at x is equal to 1.5. Okay, now let's go ahead and calculate when I is equal to 2, the value, sorry, not 2, but 1, the value of x1 is 1.5. So we are not done yet. We have to find out the value at y, value of the y at x is equal to 3. So maybe let me show you here more how many steps we need. So when I is equal to 2 here, you have xi, which is x of 2, equal to x of x0 plus I is 2, 2 times h, which is 1.5. So 2 times 1.5 is 3, plus 0 is 3 here. So here it will get the, when we get the value of the y, that would be y at x is equal to 3. So now we'll find out this k1 here, then the k2 and the y2. And that would be the approximated value at y is equal to, or y at x is equal to 3. Okay, I hope it's clear. If it's not, please let me know. I'm reading your messages. You can just type it also and let me know where to stop or the page number. So now we have here y1 is 4.302, and if we go ahead and calculate k1 for this step, now we have here at the function value at the point x1 comma y1. So we'll have here f of x1 is 1.5 comma y1 is 4.302, and we'll put these values inside our function now, which is 3e to the power minus 1.5 minus 0.4 times y, which is 4.302, and this is equal to minus 1.0519. So we just got this value here, which is minus 1.0519. Now we'll find out k2, that is the function value at x1 plus h comma y1 plus k1 times h, and we have here x1 is 1.5 and plus h is 1.5 again, y1 is 4.302 plus k1, we just got the value of k1 here. This is the value of k1, which is minus 1.0519 times h, that's 1.5. So this actually means the value of the function at the point 1.5 plus 1.5, which is 3, comma 4.302 plus this value is multiplied, you will get here 2.726, and when you put them in the function, you will get here 3e to the power minus x, which is 3, minus 0.4 times y, that's 2.726, which is equal to minus 0.9406. We've just calculated the k2 value, that is minus 0.9406. Now we'll calculate y2. So that is y1 plus half times k1 plus half times k2 times h. So you have your y1 value, which is 4.302 plus half times k1, that's minus 1.0519 plus half times k2, that is here, minus 0.9406 times h, that's 1.5, and this will give us the value 2.808, which is now the value of y, approximately the value of y and when x is equal to 3. So that's here we have 2.808. So now if you're doing this in the exam, maybe at the end you should write it like y of 3 is approximately equal to 2.808. That would be your final answer. Is there any doubt in the Hoynes method example? If you do not draw the table, you will be confused which values these are for here, these values here. So it's always better to draw the table. Any doubts? No. Okay, great. Okay, great. So now we'll go ahead and solve an example. Okay, before we solve an example for the midpoint row, maybe I'll give you the values. So already in the Euler's method, I showed you that we had the exact value of the same function there at y of 3, which was 2.763. So the true or the absolute relative true error here we'll get is 1.63% for using the Hoynes method here. Now for the midpoint, we'll do an example now for the midpoint method. So here we have the function dy by dx is 3e to the power minus x minus 0.4y, and the initial condition is y at x0 is equal to 5 here, and again we have to find out the value of the y at x is equal to 3 with step size again of 1.5. So okay, maybe first then I should write down the formulas that we're going to use here for the midpoint rule. So I'll take this here. Okay, so now we have to calculate the value. First we have for I is equal to 0 the values for x0 we get given, that's 0 here. So here we're given x0 and y0, and y0 is equal to 5, and that's it, the values that we need here. So if we start with k1, we'll have the function at x0 y0, which is the function at 0 comma 5. So we'll replace the values here. So 3e to the power minus x minus 0.4 times y, and that will give us the value 1 here for k1, and for k2 we'll have the function at x0 plus half times h comma y0 plus half times k1 times h. So we have f of x0 is 0 plus half times h is 1.5, comma we have y0, that's 5, plus half times k1, we just calculated here, is equal to 1 times h, and the value of h is 1.5 here. So that's the function value at 1 half times 1.5 here, so it will be 0.75 comma 5.75. Now if we write it down here in the function, we have 3e to the power minus 0.75 minus 0.4 times y, which is 5.75 here, and that gives us the value 0.8829. So minus 0.8829. That's the value for K2, and now we have to find the value for Y1. So Y1 is equal to Y0 plus K2 times H, and we know that Y0 is equal to 5 plus K2 is what we just found out, that was minus 0.8829 times h, that's 1.5, and this is equal to 3.676, and here this is equivalent or approximately the value of y at x1. So again, I'll draw the table down here for the midpoint rule now. So we have here okay. So we have values of I, xi, k1, k2, and yi. When I is equal to 0, xi was 0 and yi or y0 is 5. When I is equal to 1, x1 is 0 plus I, which is 1, times h, which is 1.5, and that will give us 1.5. And then when I is equal to 2, it will be x0 plus I, that's 2, times h, which is 1.5, that's equal to 3. So here we have just calculated the values of k1 is 1, k2 is minus 0.8829. So here for when I is equal to 1, we have k1 as 1, and here we have minus 0.8829, and y1 is 3.676. So this is approximately y at the value x of 1, which is y, and x1 is 1.5. So this is the value of y at x is equal to 1.5. Now we'll go ahead for the next calculation here. So we have I is equal to 1 now, and we'll, sorry, is it 1? Yep. When I is equal to 1, we have x1 is equal to 1.5 and y1. So these are the values we'll use to calculate the values of x2, y2 and all of that. Basically y2, because x1, x2 is easy to find out. So we have y1 that we just got here is 3.676 here. Now we have to find out the value of k1, which is the function at x1 comma y1. So you have function at x1, which is 1.5 comma y1, 3.676 here. And if you put that in the function, you have 3e to the power minus 1.5 minus 0.4 times 3.676 here, and that will give you the value as minus 0.8009. Okay, now can you calculate the value of k2 and give me? Try calculating the value of k2 and give me, and while I'll do also the work, because we need to hurry up a bit so we can finish everything by today. And here we have k2, where the function we have at x1 plus half times h comma y1 plus half times k1 times h here. So we have the function x1 is 1.5 plus half times h, that's 1.5, comma we have y1, that's 3.676 plus half times k1 value, which is here. We have here minus 0.8009 times 1.5, which means the function value at 2.25 comma 3.075. And got answer from Balkis. Yes, you're correct. That's correct answer, Balkis. Thank you. Now I want someone of you to calculate the value for y2. Okay, so we put this value now here. We have 3e to the power minus 2.25 and minus 0.4 times y, that's 3.075. We'll have the value as minus 0.9138 here. So that's the value for k2, and now we'll find out y2, which is y1 plus k2 times h. So you have y1 is 3.767 plus k2 is minus 0.9138 times h is 1.5, and that gives us the value as, okay, maybe that's correct. I didn't still get a value of y2. Okay, 2.30453. Okay, I get a bit different answer here. Not sure why is the difference. So we have 2.304. I have one decimal point different from you all. Should be 5 according to you. You're sure, right? All of you are giving me this answer, so I'll just replace mine. So I'll replace this with 5 here now. 3053. Yep. And that's approximately value of y at x is equal to 3, because if we write it down here now, we have k1 minus 0.8009 minus 0.9138, and here we have 2.3053, which is the value of y at x is equal to 3. Okay, and then now if you remember, the exact value was 2.763 of this one here at y is equal to 3. So we have the relative approximate, not approximate, relative, absolute relative true error is equal to 16.5%. So the midpoint rule, the error seems to have increased than the Heinz method. Okay, until now, is everything clear? Yes. Okay. Great. So now let's go ahead to Rangakuta fourth order method. So what we did until now was Rangakuta second order method, and now we are in the Rangakuta fourth order method. And Rangakuta fourth order method is based on the first 5 terms of the Taylor series. So what we are trying to solve here is first order ordinary differential equation, which is of the form dy by dx is equal to the function at x comma y with an initial condition given to us where y of 0 is the value at y0. So the first 5 terms of the Taylor series will look like this here. So it would be yi plus 1 is equal to yi plus dy by dx at xi yi from xi plus 1 to xi, plus we have 1 over 2 factorial d square y divided by dx squared at xi yi here, and from xi plus 1 to xi squared. And then we have plus 1 over 3 factorial d cube y divided by dx cubed at xi yi from xi plus 1 to xi cubed, plus 1 over 4 factorial d 4y over dx to the power 4 at xi yi from xi plus 1 to xi to the power 4 plus order of xi plus 1 minus xi to the power 5. And in Rank-Kutta second order method, you take the first three terms of the Taylor series expansion and you equate it to what Rank-Kutta assumed to be the formula for numerically solving the differential equation of this form. Now in Rank-Kutta fourth order method, we are adding two more terms of the Taylor series here. So we are taking first 5 terms of the Taylor series, and now since we already know that dy by dx is f of xy, we'll replace or we'll substitute this value in the Taylor series here, and that will give us the formula yi plus 1 is equal to yi plus, so replacing dy by dx, we'll get here f of xi yi times h. So this is the step size here. We can replace here this one by h squared and so on. So here we'll have h plus 1 over 2 factorial, the first derivative of the function at xi yi h squared plus we have half, or sorry, 1 over 3 factorial f double prime xi yi h cubed here now plus 1 over 4 factorial f 3 prime xi yi h to the power 4. So that's the first 5 terms of the Taylor series. So instead of finding the f prime, f double prime and f 3 prime, what Rank-Kutta did was they assumed the formula to be yi plus 1 is equal to yi plus a1 times k1 plus a2 times k2 plus a3 times k3 plus a4 times k4 times h. So they then equated this form to the previous form here. So they equated this one here, what they assumed the formula to be, to the Taylor series up here, and they came up with the formula where you're not required to calculate the derivatives, the first derivative, second derivative, or the third derivatives of the function. So you're just calculating the values of the function at certain points, right? So we're just only calculating the function at some points but not calculating the derivatives here, and that's now called the Rank-Kutta fourth order method, or you can call it RK4 method. So there was different versions of method discovered even in the Rank-Kutta fourth order method. Just like Rank-Kutta second order method, we had points, we had midpoint, and there are more Ralston and more. But then even for this, we have more than one version, but we only study RK4 method for the Rank-Kutta fourth order method. And the formula for this one here is yi plus 1 is equal to yi plus 1 divided by 6 times we have k1 plus 2 times k2 plus 2 times k3 plus k4 times h. So you're given here the weightage as 1, 2, 2 and 1, which is 6, and you're dividing here by 6 to them. And here now the k1 is the value of the function at xi, yi, and k2 is the value of the function at the point xi plus half times h, comma, yi plus half times k1 times h. And then for k3 we have the function value at xi plus half times h, yi plus half times k2 here now times h. And k4 we have f of xi plus h, comma, yi plus k3 times h. So now that's the formula for the RK4 method, and let's start solving an example to make this more clear to you all. So we have the function here dy by dx is equal to 3e to the power minus x minus 0.4 times y, and the initial condition is same again, so we have y0 is equal to 5, and we have to find y at the value of x is equal to 3 using step size h is equal to 1.5. So now we start by finding out the value for k1. So here let's write first the value of I. When I is equal to 0, you have k1, you have x0 is equal to 0, and you have y0 is equal to 5, and your h is equal to 1.5 here. So k1 is equal to the function value at x0, comma, y0, which is the function at 0, comma, 5. So you have 3e to the power minus 0 minus 0.4 times y, which is 5, and this gives us the value 1. Now value of k2, we have the function at x0 plus half times h, comma, y0 plus half times k1 times h. So we'll have here the function at x0 is 0 plus half times h is 1.5, comma, y0 is 5 plus half times k1. So we just found out the value of k1 here, which is 1 times h is 1.5. So now if we rewrite that, we'll have here 0 plus half times 1.5, which is 0.75, comma, we have here 5 plus half times 1 times 1.5, which is 5.75. So if we put that in the function, we have 3e to the power minus x here, minus 0.4 times y, which is equal to minus 0.8829. That's the value of K2. And now we'll go ahead and find out the value for K1. Sorry, K3. So we have here f of x0 plus 1 half times h, comma, y0 plus 1 half times k2h. So f of x0 is 0 plus 1 half times h is 1.5. And we have here y0, which is 5 plus 1 half times k2. So we just got the value of k2 here, which was minus 0.8829. So it's minus 0.8829 times h here, so it's 1.5, and that would be f of this one here is 0.75. And when you calculate this part here, you get 4.338. And now if you replace these two values as x and y in the function, you will get here 3e to the power minus x, which is 0.75, plus we have, sorry, not plus, minus 0.4 times y, which is 4.338, and that will give us the value minus 0.3180. That's the value for K3. Now if you calculate the value for Y1, not yet, sorry, we have to now calculate the value for K4. It's a bit lengthy, right? So now we have to calculate the value for K4, where the formula is f of x0 plus h, comma, y0 plus K3 now will be utilized in K4, so we have times h, and this one here will be equal to f of x0, we know as 0, plus h is 1.5, and we have comma, y0 is 5 plus K3, that value that we just got is minus 0.3180 times h is 1.5, and this gives us the function at this one here is 1.5, and this one if you calculate you'll get 4.523. So the function at x value 1.5 and y value 4.523, if you put it in our f of xy, you will get 3e to the power minus x, which is 5, minus 0.4 times y, that's 4.523, and that gives us the value as minus 1.140 here. So now if we are, let's write down all the values of K1, K2, K3, K4. So K1 we got as 1, K2 we got minus 0.8829, K3 is equal to minus 0.3180, and K4 is equal to minus 1.140. So why did I write this down is because we need all of these values now to calculate y1. So y1, the formula is y0 plus 1 over 6 times k1 plus 2 times k2 plus 2 times k3 plus k4 times h. So y0 is 5 plus 1 over 6 times, we have K1 is 1 plus 2 times K2, that's 0.8829, plus 2 times K3, which is minus 0.3180, plus we have K4, that's minus 1.140, and the whole thing multiplied to H, which is 1.5. So this here, if you solve, you get 4.365, which is approximately the value of y at x is equal to 1, and we know that x0 is 0, so x1 is x0 plus I times h. So we have x0 is 0 plus I is 1 here now, so 1 times h is 1.5. So you have x1 is equal to 1.5. So this is approximately the value at y is equal to y, the value of y at x is equal to 1.5. Okay, now we have to calculate y of 3, so we have to go one more step ahead. And yep, maybe I'll draw the table at the end here now. So we'll have okay. So we have values of I, values of xi, k1. Uh-oh. We have more values here to take. So we have I, xi, k1, k2, k3, k4, and yi. So we have here I, xi, and then k1, k2, k3, k4, and yi. So when I is equal to 0, xi is 0 and yi is 5 here. When I is equal to 1, xi is, so calculating the values of x0 is 0, x1 is x, okay, let me write the formula above. So we have xi plus 1 is x0 plus I times h. So we have here 0 plus 1 times 1.5, which is equal to 1.5, and x2 is 0 plus 2 times 1.5, which is equal to 3. So here we have 0, 1.5, and 3, and we need the value of y when x is equal to 3 here. So that's the number of steps that we need to do for this one here particularly. Now we have got the values of k1 as 1, k2, k3, k4 here, and even y1. Let me write the values here down now. So we have here 1 minus 0.8829 minus 0.3180 minus 1.140, and y1 is 4.365. Now let's go ahead and calculate for k1. So we have I is equal to 1, x1 is equal to 1.5, y1 is equal to 4.365, and h is equal to 1.5 here. Now k1, the formula is f of x0, y0. Sorry, not zeros here now, but ones. So here we'll have ones now. So x1, y1. Calculate the value of k1 and give me, all of you. So now here all the values of k1, k2, k3, k4 you all will calculate. So start working and give me the values. Got the values of k1 from Balkis? Yes, it's correct. It's correct. So we have here f of 1.5 comma y1, which is 4.365, and if you put that in the function, 3e to the power minus 1.5 minus 0.4 times 4.365, this will give us the value minus 1.076. Now I want answers for K2. The formula for K2 is the function value at x1 plus 1/2 times h, comma, or okay, y1 plus 1/2 times k1 times h. So give me the value for K2. It somewhere look correct, but it's just a bit different from mine, very slight difference. But what about the rest of you? Only Balkis is giving me the answers. I want answers from more students. We have 39 people here. Ryan, okay. Others? So here we have f of x1 is 1.5 plus half times h, that's 1.5, comma y1, which is 4.365 plus half times k1, which we just got the value as 1.076 here, times h, that's 1.5. So we have here the function at 2.25 comma 3.557. So if we put that now inside our function value, we have 3 times e to the power minus x, that's 2.25, minus 0.4 times y, that's 3.557, and that gives us the value as minus 1.0107. So that's K2, this is K1. Now for K3, May al-Balushi, yes, that's the value for K3. At least when you're writing the value, say me it's the value for what. So you just write K3 is equal to this or something like that. Be more accurate. But it's correct for May also, it's correct for Balkis also. It's just you're rounding up to different decimal places. So we have K3 is the function at x1 plus half times h, comma, y1 plus half times k2 times h. So we have here the function at x1 is 1.5 plus 1 half times h, that's 1.5, and plus we have y1, which is 4.365 plus 1 half times k2 value, that's minus 1.107 times h, which is 1.5, and then we have the function at 2.25 comma 3.535. So if you have here 3e to the power minus x minus 0.4 times 3.535, which is equal to minus 1.098 here. Okay, now the value for K4. So I'll give you the formula, which is f of x1 plus h, comma, y1 plus k3 times h. K4 is minus 0.938. Yes, that's correct, Balkis. That's correct answer. So we have here f of x1, that's 1.5 plus h, which is 1.5, comma, y1 is 4.365 plus k3, which is minus 1.098 times h, 1.5. To simplify that, you get the function at 3, 2.718, which is equal to 3e to the power minus 3 minus 0.4 times 2.718, which is equal to minus 0.9379. Now we got K1, K2, K3, K4, so we can calculate Y2 now, which is Y1 plus 1 over 6 times K1 plus 2 times K2 plus 2 times K3 plus K4 times H. Can you give me the value for Y2 now? So we got value from Hiba 3.92925. I have actually much different answer. Yeah, Balkis, you're having 2.759. That's the answer that I have. That's correct. So Hiba, maybe there is slight mistake in your answer. Somewhere you did a mistake in the calculation. So we'll have here y1 is 4. Okay, I'll just write it down maybe. So here y1 is 4.365 plus 1 over 6 times K1 is minus 1.076, plus we have 2 times K2, which is minus 1.107, plus 2 times minus 1.098, plus K4, that's minus 0.9379, times H, which is 1.5. So that gives us the value as 2.759. That's the value for Y2. And if we write this all in the table, we'll have here K1 is minus 1.076, K2 is minus 1.107, K3 is minus 1.098, minus 0.9379, and then we have here 2.759. Okay, so that's the value that we are searching for at y of 3, right? Now here the exact value of the function at y of 3 is actually 2.763. So the absolute relative true error is true value, the exact value 2.763 minus the approximated value here, which is 2.759, divided by 2.763 times 100, and that gives us an error percentage of 0.1507%. So the Rankuta order 4 method has brought down the error from 1.6 or 16 point something to just 0.15%. So showing that this is a much better method than the other methods of solving ordinary differential equations that we have learned up till now. Okay, so that's the end of today's lecture, the last lecture.